Okay, so welcome to another IAU G2 Massive Star Seminar. My name is Aida Wolford. I'm a professor at IAU and I'll be your host today. So today we have Ryan Lau, who's an associate scientist at Caltech in Pasadena, California. And he will tell us about tracing stellar explosions and cosmic dust. But before we start, I would like to say a few words about his background. His research interests are in infrared transient time domain, dust, massive and evolved stars, high mass X-ray binaries, and ultra-luminous X-ray sources, the galactic center of star formation. He got his PhD in 2014 from Cornell University. And he has held several academic positions in the US and Japan. And previously, he was an assistant astronomer at NORAD Lab in Tucson, Arizona. But he also was a JAXA International Top Young Fellow at Sagamihara, Japan. I don't know if I pronounced that correctly.
No, that was pretty good.
So Ryan, I will let you know when there are 5 minutes before the end of the time for your talk.
All
Welcome.
right. Yeah. Thanks so much, Ida, for the awesome introduction. And thanks, Sergio and Ida, for the invitation to give this talk. I'm really excited to give it. Yeah, my name is Ryan Lau. I'm a staff scientist at IPAC, Caltech. Uh, I'm going to talk to you folks today about tracing stellar explosions and cosmic dust. So primarily, my talk is going to focus on these observations that you see here with JWST of WR140. And we actually have multiple observations of this, so we can make this nice little movie of these shells expanding. So we'll get into that later. Okay, I'll just start off with a quick outline of my talk. So first, I'll go through the background motivation of what drives this kind of major science question here. And this is primarily focused on revisiting the life cycle of stars and dust, stellar explosions, and also studying the origins of dust. So that's been kind of my primary research question is tracing the origins of dust in the interstellar medium, which is one of these outstanding questions of kind of exploring and understanding our cosmic origins. The specific sources I study, or the thing I've been focusing on in the past couple of years, is trying to revisit the impact of dust production and mass loss from these massive evolved stars called Wolf-Rayet stars. And I'll talk about it. Primarily, this is going to be the main focus of the talk, is science results of our observations of dusty Wolf-Rayet stars with the James Webb Space Telescope. And then the last part of the talk, I'll give kind of a perspective on the future outlook of infrared time domain astronomy with these new platforms that are going to be coming online very soon. Like the Vera C Rubin Observatory was just entered its operations phase, so very excited about that. And the Nancy Grace Roman Space Telescope, which is going to be launching probably within the next year or so. So lots of exciting infrared and time domain astronomy to be enabled in the next couple of years. Okay, so just to start off, this is kind of our Astro 101 picture of star formation. So we have everything kind of starting off in this dusty giant molecular cloud star forming nebula region. And through some kind of gravitational perturbation, maybe a supernova shock propagating through the cloud, you get this cloud to collapse into dense, dusty, gaseous cores. And depending on the mass of those cores, you can either follow the sun-like star track here on the left, or if you're over about 8 solar masses, you go through this massive star track, which is the one that I'm particularly interested in. Maybe most of the folks here are too. So I'll primarily focus on this. So we have a massive star which lives on its main sequence phase, burning hydrogen in its core for on the order of tens of millions of years, maybe even less than that, depending on how massive it is. And then maybe at the end of its main sequence lifetime, when it runs out of hydrogen in its core, starts burning hydrogen in its shell, puffs up, and could become a red supergiant. where it produces a lot of could produce a lot of dust and also eject a lot of gas into its surrounding environment. At the end of this phase, it's kind of post-main sequence phase, we could get an explosion as a core collapse supernova, where all this kind of metal-enriched innards in the core of this massive star gets ejected into the interstellar medium, and then leaving behind this inert, dense core, either a neutron star or a black hole, depending on the mass of that core. And then this material that's been ejected through the red giant phase, red supergiant phase, or the supernova, goes back into the interstellar medium to form future generations of stars. So that's kind of the basic picture of this, but it kind of misses one key thing that we now know is that most stars, massive stars, should have very close binary companions. So close, in fact, they should be exchanging mass over their lifetimes. And this changes things quite a bit because the mass of the star is what really drives its evolution. And if you have a star exchanging mass with a companion, that can radically alter the trajectory it takes in its evolution. So instead of seeing this particular track like this, you can get different evolutionary pathways. When the primary star leaves the main sequence and puffs up as a red supergiant, it could fill up its Roche lobe and start donating mass to the secondary. Um, if it's close enough, if it's a close enough binary, you could get a common envelope phase as the primary evolves, which can cause a merger of the two stars, or you could get a detached system after this phase. So, or if they're sufficiently separated, you could have these evolve effectively as single stars. But this should be the actually quite rare. So most of the time, these master stars should interact with each other over their lifetimes. Okay, so because you have this different branching evolutionary pathways for these master stars, it affects how they evolve, it affects how they lose mass, and should also affect how they explode or how they erupt over their lifetimes. So basically the typical types of stellar explosions, the end of lifetime explosions of these massive stars or other types of transients, you have novae or supernovae. Novae, maybe not for massive stars, but just to show the kind of typical stellar explosions. So this is showing a light curve in the mid-infrared here of different types of supernovae and novae as a function of time. So time on the x-axis, and then mid-infrared absolute luminosity on the y-axis. But there have been these emerging classes of infrared luminous transients, things that aren't quite as luminous as supernovae, but brighter than novae. They've kind of also been dubbed gap transients since it fills this gap between novae and supernovae. We have luminous red novae, or stellar mergers, which is likely what's the astrophysical mechanism that explains their outbursts. So two stars merging with each other. There's also luminous blue variable eruptions, or these massive, dusty, gaseous outbursts from massive evolved stars. Although the mechanism isn't quite well known yet, what exactly drives these outbursts, but these appear to have very dusty infrared luminous signatures. The thing that I'm going to be focusing on in this talk are these outbursts from colliding wind Wolf-Rayet binaries that can produce significant quantities of dust and also have very strong signatures in the infrared. And then what's also kind of cool is that kilonovae, or neutron star mergers, also appear to have a very long-lived infrared component, as you can see here in these images. So while the optical emission from kilonovae drops off fairly rapidly within the first couple days, the infrared emission is much more long-lived. And so studying these is of interest to do in the infrared. And that's kind of emphasized by this detection of 170817, which was the first neutron star merger observed at electromagnetic wavelengths, or electromagnetic counterpart. You can see that here with Spitzer at 43 days after the gravitational wave event. And so here's the kilonova on this light curve. And yeah, just to point out too that Spitzer has really been doing a lot of this, had been doing a lot of this interesting work to explore the landscape of infraluminous transients. Unfortunately, Spitzer is no longer operating, but in the near future, we'll have Roman and also Rubin to kind of step up to do these studies. Okay, so there's kind of two key things that I want to point out here about uh, the whole background that I set up about this. The one thing is that these infrared time domain observations have opened up this window to investigate the dusty and obscured lives and deaths of massive stars. The second thing, I mentioned dust quite a bit already in the intro, but we have dust formation from different phases of this massive star's life, and its red supergiant phase. It can eject dust and gas, and then in the supernova, you have this metal-enriched ejecta that can go on to form copious amounts of dust. So it's a key component in the stellar life cycle, and also in the interstellar medium. It's where these stars are forming from. But there's still this big question, this big mystery of where this dust actually comes from. What's the origin of the dust that we see in these galaxies, in the ISM of these galaxies, especially at the early universe? And it's particularly exacerbated by these newish observations from ALMA and JWST that see copious amounts of dust in galaxies within the first gigayear of cosmic time. So, because you have so much dust this early on, it's likely that it's coming from massive stars because they evolve on rapid timescales on the order of millions of years. Whereas if you're looking at dust production from low mass stars, those primarily form dust like in their asymptotic giant branch phase. That takes on the order of billions of years to get to that point. So those are too slow. You need some kind of rapid dust formation factory to explain what's seen here. Now, the leading theory for this has been supernovae, which makes sense. They also evolve very rapidly, and you expect that at the end of a massive star's lifetime. You have the metal-enriched ejecta, and they seem to form a lot of dust. But it's still highly debated because of the dust destruction that you can also get from the supernova shock, both the forward shock being driven into the ISM and the reverse shock being driven back into the newly formed dust in the ejecta. So still a lot of questions, but still a very promising source of dust. Okay, so this research that I'm doing, that's kind of this connection between these two very interrelated themes of stellar evolution and the origin and formation of dust. And so I've kind of been kind of treading the line between these two different research questions on stellar evolution and dust production. And in order to do this, it's I've been combining infrared and time domain observations to study dust stellar evolution and our kind of explosive cosmic origins, using ground and space-based facilities, and also planning to use these upcoming ones with Rubin and Roman. And these are the types of transients I'm interested in. And the one I'll talk about next are these outbursts from colliding wind Wolf-Rayet binaries. Okay, so what exactly is a Wolf-Rayet star, and how exactly do they form dust? So Wolf-Rayet star is a descendant of a massive O star, probably greater than about, with an initial mass greater than about 20 solar masses. These are characterized by very high luminosities, greater than 10 to the 5 solar luminosities. They're very hot because we're looking at kind of the inner helium core from these massive stars that have lost most of their hydrogen envelope. So they can be greater than 40,000 Kelvin. They have very strong winds and also very high mass loss rates. So these are very some of the most extreme stars that we know of. And so you might be wondering, okay, we have this super hot, luminous environment with these intense winds and high mass loss rates. How can we form dust around these stars or in this hostile environment? Because typically, you expect dust formation perhaps to occur in the slow, gentle outflows from asymptotic giant branch stars, where they're moving at tens of kilometers a second, maybe even less than that. The photospheres of those stars are much cooler, like 3,000 Kelvin and not 40,000 Kelvin. And this is almost the exact opposite of that. And so the key to this seems to be the presence of a binary companion, where you can actually have colliding winds between the primary Wolf-Rayet star and the companion star, typically an O or B type star. And it's the compression between those two winds that enables that you can actually reach the right densities for dust formation. You get the self-shielding from the optical UV photons from the Wolf-Rayet star, and downstream from that win-win collision region, you get the right conditions where you can get dust formation. So that seems to be a key component in enabling dust formation around Wolf-Rayet stars. And for some reason too, probably because of just for chemistry reasons, it's only the carbon-rich Wolf-Rayet stars that appear to form dust. So you have different flavors of Wolf-Rayet stars. You have nitrogen-rich ones, and then you have the WNs, and then you have the oxygen-rich ones, the WO, and then the carbon-rich ones, the WC. And only WC stars appear to form dust in this kind of colliding wind mechanism. But they can form fairly copious amounts of dust. They can be prolific dust makers, producing around 4 times 10 to the minus 6 solar masses of dust per year. Just to put that number into context, the total or all of the AGB stars in the Large Magellanic Cloud, their combined dust production rate is about 10 to the minus 5 solar masses a year. So if we just have a few of these heavy dust makers, these heavy carbon-rich Wolf-Rayet binary dust makers, that could be comparable to the entire population, dust input from the population of AGB stars. So the point I'm trying to make is that it only takes a couple of these to really impact the dust budgets in the ISM of their host galaxies. And that's my main research interest into these is potential dust factories, perhaps in the local and the early universe. Since these check a couple of boxes here, they evolve on very rapid timescales. In fact, you should get these before you get supernovae, and they can form copious amounts of dust. And even if you think of the end fates of a Wolf-Rayet star, they may collapse directly into black holes, although that's still very highly debated. And then you might not need to worry about the subsequent supernova shock destroying all the dust that's formed by the Wolf-Rayet star. So a pretty appealing source for an early source of dust. Okay, and so to study this, we've been using the James Webb Space Telescope. In fact, we were one of the first programs in this early release science um, phase of JWST to get data on the platform. So we're super excited about this. A couple of years back when we were getting data. Here's our team. In fact, I think a couple of our team members are on here on this call. Um, Part of what was really important about having such a diverse team is we were really it was really crucial to have the prep work going into this, and so we understood and were able to like write effective papers on our first results here. So it's been really a great team to work with, and we're still doing some really interesting science with JBST on these Wolf-Rayet stars. So to kind of like give an overview of what we're doing, we want to look at the dust formation from these WC stars and to investigate the chemistry. Since with JWST, we're able to do things that we haven't been able to do previously, which is the spatial resolution that we get and the sensitivity and the spectroscopic mode that we can get resolving, spatially resolving the star from the dust shells. So we're looking at the composition and formation, which includes studying the morphology of these dust shells as they form in this colliding wind binaries, um, using the nearest aperture masking interferometry mode, which is kind of a cool mode on JWST, and using the IFU, the MRS on the MIRI instrument. We also want to look a little further out, not just to the inner morphology, but to study how dust grows and is destroyed as it's propagating outwards into the ISM. And so we also use the MRS and the imager to do this. So we had a paper that we published last year using this instrument mode, which is really fun because this is I think the first time that any type of infrared interferometry has been done in space. So we have those results out, investigating the morphology of one of these colliding wind Wolf-Rayet binaries using aperture masking interferometry. We also have a couple of papers. One of these just came out, I think, yeah, just a couple of days ago, by Kotomi Taniguchi at NAOJ, looking at the pH or AIB emission from these complex hydrocarbons produced from these Wolf-Rayet stars. Okay, so just to step back a little bit, this was our primary target, WR140, which has been dubbed the Rosetta Stone of colliding wind binaries. And the reason for that is it's been studied so well over like the past 50 years. Its orbit is very well characterized. I think the two stars have actually been spatially resolved with ground-based interferometry. There have been radio observations that spatially resolve the colliding wind region of the two stars. So At almost every wavelength, with almost every kind of observing mode, this system has been studied. And so it's very well characterized. We know that it's a WC7 subtype, that's the carbon-rich Wolf-Rayet star, and that its companion is an O5 star. It's highly eccentric, as you can kind of see here from its orbit. And we have some pretty nice ground-based observations that we took with the COMEX instrument on the Subaru telescope back in 2020. So this is just showing here, this is the core of the star of the binary here, and then this is the dust shell that forms as the O star and the Wolf-Rayet star kind of go through periastron passage. It forms this shell of dust every 8 years. And so because it's so well characterized, it's like almost the perfect angular resolution too to get JWST observations of this. It really is this ideal laboratory for investigating colliding wind dust formation, not just at infrared wavelengths, but in a bunch of different wavelengths. This has been one of the prototypes to try to study this mechanism. All right, so I'll zoom in a little bit more on this figure or on this image here because this was the best image at this wavelength that we had of WR140, or this is one of the best that we had in the infrared at about 10 microns to study the spatially resolved structure of this dust shell. So that was until we got observations with JWST, where we didn't just see one shell, we saw over a dozen of these dust shells that formed over the past like 200 years of dust formation in this colliding wind binary system. So every 8 years, we have this dust shell that formed. And so we can see the sequence of past dust formation episodes from WR140, which totally blew us away. We thought something went wrong with our data because typically when you see rings like this from your observations, it's not usually a good thing. So it took a little bit to sink in what we're actually looking at here. But of course, we wanted to be 100% sure that what we're looking at was astrophysical and not just some weird artifact. So the first thing that we did is we wanted to plot what does the PSF look like from JWST? Like, because we know that not all of this is real. So that this stuff here, like that this is coming from the PSF diffraction pattern. So we overlaid that and we were able to identify what we thought that these diffraction spikes here are indeed coming from the PSF and not related to something that's astrophysical. Uh, so that's nice, but that means that everything else here is real. So including this interesting looking structure here, that's also, looks like it could be a diffraction spike, but it's asymmetric, so that's kind of a giveaway. And yeah, it doesn't seem to match any part of the pattern that we see in the PSF. All right, so that's nice, but if you're looking at some of the first data from a new observatory, we want to be like super, super sure. So we took it one step further, and fortunately, at a similar time that we're looking at this data, there was a grad student in Australia, Yinwo Han, who's now a postdoc at Caltech. He has been working on ground-based high angular resolution data of WR140, and he produced these really amazing geometric models of WR140. And it just was a very fortuitous timing where we were able to ask him, okay, your models look amazing. What happens if we run your models and we just stack together 20 dust shells? What does that look like? And how does it compare with the images that we see with JWST? And so those are the models on the right. And we were kind of blown away at how well this matched because there's no tuning at all to his models. This is all from the ground-based parameters. And we just asked him to just let it run for 20 cycles. And it matched almost perfectly with our observations, all the way down to this kind of linear feature here, which is due to the limb brightening effects that you get from stacking multiple shells together. You see the limb brightened edge of the shells, and it kind of blends together as this linear kind of spear-shaped feature cutting through in this direction. So we see that in our data, and it's reproduced fairly well with the models. Even the shell spacings kind of matched up pretty well there. It was, yeah, we were quite taken aback with how well this worked out because things don't usually work out this well when you try to explain something with a model. Okay, and so we went back to look at this in cycle two, so we can actually put a movie together of this. And these are these observations here. This was published earlier this year by Emma Lieb, who's a grad student at University of Denver, working with myself and Jennifer Hoffman. And so this is like just clear confirmation that these dust shells are real. We saw them expanding at exactly the expansion velocity we expected. And you can see that that linear feature is also present in the follow-up observations, while you see the PSF rotating because of the different position angle between cycle one and cycle two, which is what you'd expect from the different position angles. So yeah, this is just super cool for us to see all the shells that we detected in the first observation. We see them in the second one, except expanded by a little bit more. It also helps us too because it confirms a lot of the substructure that we see within the shells has persisted in the second epoch that we observed it. So a lot of the substructure that we're seeing, we can confirm that it's not due to any artifacts that we saw from the first image. So yeah, really a lot of cool stuff they were able to get just with the imaging from the first two cycles. Okay, so that's kind of just half the science that we're able to do with our data set. Um, if you remember, one of the main things that I mentioned we're looking at is studying the chemistry, looking for any of the precursors of the carbon-rich dust that forms. And so this is what we did with the MRS IFU data. So this is spatially resolved spectroscopy that we got from the central region and also the second offset here too to cover the first and second and also part of the third shell of WR140. So these are the MRS observations here. So these are spatially resolved spectroscopy observations all the way from about 5 microns to about 28 microns. And what we saw are these features that are there's very many there's different names for these features. Unidentified infrared bands, aromatic infrared bands, but these are typically attributed to polycyclic aromatic hydrocarbons or PHs, and they exhibit strong prominent infrared features at about 6.2 microns and also 7.7 microns. So when we saw this pop out from the dust shell around WR140, we knew right away, okay, like this is pH emission. This kind of confirms that this is carbon-rich aromatics that's composing these dust shells. There's a couple interesting things about this, like this feature here is at 6.4 microns, which is slightly shifted a little bit towards longer wavelengths from the standard 6.2 micron. And Kotomi Taniguchi, who's a professor at NAOJ, just recently published this paper on this. So if there's more interest in that, definitely check that out. And so, yeah, we're pretty excited from this result that it is composed of this carbon-rich aromatic compounds that we could kind of expected carbon-rich, but we weren't sure if we're going to detect these pH features. And so that was a nice confirmation of that with that detection. And so, kind of concurrently, there's been more JWST observations of like early universe high redshift galaxies that showed this interesting absorption extinction bump here that's typically associated with the presence of carbonaceous dust and PAHs. So totally different observations. Just this is of galaxies in the first gigayear of cosmic time, but they show this 2175 angstrom bump associated with pHs, and so that really highlights the importance of understanding like where is all this dust coming from. And so since we found that dusty Wolf-Rayet stars can form pHs, we know that these evolve very quickly. Perhaps these could be one of the leading sources of pHs at such early times. So yeah, even more motivation to try to explore this avenue of carbon-rich dust production. There's still a lot of work to be done, but yeah, we're really excited about trying to pursue this. Okay. So there, of course, there's surprises with new data or new observations. We got a lot of things that we didn't quite expect. This is still a work in progress, but we feel pretty confident about these results. One weird thing that we saw in our MRS data cube, while we're looking around this sulfur 4 emission line, so this forbidden emission line, we saw this weird ripples in the data here. So if you look at where this red arrow is pointing, yeah, you see these weird as we go through scroll through velocity space, there's just something that looked strange as we're looking through it. So we talked to all the Miri instrument experts on our team, and they've never seen any kind of artifact like this in their data. So it was like, okay, this must be real, but what exactly are we looking at here? So we took this and we subtracted the continuum to just plot like an emission line map. And this is just scrolling through velocity space um, of uh, of the sulfur 4 line. And we see this really interesting uh, 3D velocity structure around WR140 here. And we're hypothesizing that we're actually resolving and detecting the wind from the Wolf-Rayet star. And it kind of matches in the colliding wind pattern or morphology that you would expect. So again, that's not, this is, we were looking at it and like, that's probably what it is, but you really want a model to back it up. And this is a little bit more complicated to do than just a geometric model. So Chris Russell, who's at the University of Delaware, had been working on similar data or similar models at the time. So again, just fortuitous timing. And here are his hydrodynamic simulations of WR140 on the right. Again, not even really tuning the parameters too much, just using parameters from previous studies. But if you compare what he sees in the simulations and our observations on the left, it's a really amazing match. You see all the structure from the shell or from the wind-wind interaction region, just from the wind, the spherically expanding wind itself, like it's reproduced very well between the hydrosim model and the observations. So just a really cool, like exciting thing that we were able to obtain with this data set that we were not expecting at all. Which I think could be the probably one of the best spatially resolved observations of a massive star wind. So we're super excited about this result. We hope to we're going to get it submitted soon because it's really cool. And yeah, this needs to be it needs to be more widely shared. There are some next steps for us. We already have this data and we're working on it. Riko Seno, who's a grad student at the University of Tokyo, is leading this paper. We got LRS spectra, so slit spectroscopy across the dust shells to look and see how these dust features evolve over time, over the past 7 shells, instead of just looking at the inner shells with the MRS. So lots of cool stuff coming from this too. And there's more dusty Wolf-Rayet stars that have been observed with JWST. This is a ground-based Vizier observation of another dusty Wolf-Rayet star. This is WR112. So really kind of like a spectacular image from the ground. But what does this look like with JWST? This is produced in a really nice publication by Noel Richardson, who's a faculty at Embry-Riddle University in Arizona. And he found these, similar to WR140, this nested sequence of dust shells showing that it's not just WR140 that exhibits this, that has this dust surviving over long time scales, but also in this source. And then here's another one. This is WR48A, taken by the T-Rex mid-infrared camera on Gemini. And this is the observation of that source with JWST. So again, you see these nested dust shells that have been forming every dust formation episode from this system here. So yeah, really cool stuff. And we put in a cycle 5 proposal to hopefully get some more spectroscopy of these sources that have been resolved with JWST. Okay, so that's the Wolf-Rayet side of these things. But where do we go from here from our JWST observations of these sources, and how do we address this question about the dust input from all types of eruptive and explosive infrared transients as we move into this era of Rubin and Roman and JWST? So that's a question that I'm pushing here. It's like, how exactly do non-supernova stellar explosions or eruptions contribute to the dust and chemical enrichment of the universe? And it's been challenging to address this question because we need a couple of things to do this kind of experiment. We need a transient discovery engine. We need facilities that are capable of classifying these things, which we have that. And we need something that can actually look in the mid-infrared to characterize the dust and ejecta. So we'll have Rubin and then Roman pretty soon to find and identify these transients. We have these nice ground-based facilities that can do follow-up spectroscopy to classify them. And we have JWST to do the characterization at mid-infrared wavelengths to see how much dust and what the chemical composition actually is. So it's this really nice exploration of infrared transient science that's enabled by Rubin, JWST, and then Roman also in the very, very near future. So this is going to be the final couple slides of the talk. Just a bit of forward-looking perspective of what we can do here. So the Vera C Rubin Observatory, this is what I worked on when I was at Norlab and something I'm very, very excited about. This is how we're going to find new, interesting optical and also infrared transients. So it's going to conduct different surveys, but this wide, fast, deep survey, which is shown here in this in the survey footprint here, which is probably a little bit out of date. But we expect to discover a number of these infrared transients, even though it only operates out to 1 micron. We expect to identify a number of these with Rubin. So we're gonna see a lot of different transients and interesting science with this facility. So lots of other things to be excited about. As an example, here's one of the targets that we identified with Spitzer. So this is a stellar merger candidate that we dubbed Spirits 18 NU. And we can expect that Rubin should be able to discover things like this, but really what you want is something in the infrared to kind of confirm that, or with deeper infrared limits where these things tend to be more luminous. So we're really excited to have Roman coming online to make sure we can identify the infrared signatures of these sources where they might be a little more promising to detect, although it's not going to have the same wide field coverage as Rubin. So it's the combination of these two, I think, is going to be what's really powerful and helps enable this science. And then I won't go into too much detail on this, but just because my work at IPAC revolves around uh, this enabling time domain astronomy with Rubin or with Roman and distributing alerts to alert brokers to let astronomers know that, hey, there's something interesting that Roman has found that's a time varying source. Um, these alert brokers and this alert distribution is going to be a crucial part of this time domain ecosystem to enable these discoveries and the follow-up. And then we can do spectroscopic classification with your favorite ground-based observatory, Keck, Palomar, Gemini, VLT. Lots of interesting facilities to use to actually follow things up in the near infrared. And then JWST to just clean up the mid-infrared to just capture all of that, the wavelengths that you need to characterize what type of dust is forming, or maybe even the chemical composition of the ejecta. Of course, it would be nice to have longer wavelengths, and hopefully we'll get that in the future with a mission like Prima. And with JWST and the combination of that with these wide field survey telescopes like Rubin and Roman, um, these are going to be crucial for us to identify and follow up things like the electromagnetic counterparts of gravitational wave events like neutron star mergers to study perhaps the lanthanide-rich ejecta of these sources. And so in the gold is showing a model of one of these kilonovae, and then the red is showing the sensitivity of JWST. So you really, really want JWST to be able to follow these things up to characterize what the heaviest elements that are being synthesized in the ejecta of these neutron star mergers. All right, so that's covering this whole transient and discovery and follow-up campaign with all these facilities. And so again, just looking forward to all the cool stuff that we can do when we have Rubin starting its surveys and when we have Roman launched. And the cool thing about this is not just an idea. We've already been doing this. There's already interesting time domain surveys that are operating, like ZTF, and we're already doing this follow-up with JWST. We have a number of programs where we've been conducting this. We have this nice GTO program. That's where the PI is Mike Ressler. And so myself and Jacob Jensen, who's another staff scientist at IPAC, we've been looking at this data set to characterize these infrared transients using NIRSPEC and MIRI. We have a program where we looked at an extragalactic outburst from a Wolf-Rayet star, Spirits 19Q. So that's in a low metallicity environment, which is of interest to us if we're trying to look at a analog environments of the early universe. Um, there's a luminous red nova program led by Viraj Karambelkar, who's a Hubble fellow at MIT, or sorry, at Columbia. And then we have this Cycle 4 program. It's a survey program where we want to do imaging observations of the known infrared transients to get a nice SED of those sources. So this is ongoing. We still haven't got any data yet, but we're hoping to get that later this year. And then we already have a number of results from these programs. So Sam Rose, who's a grad student that I've been supervising here at Caltech, she's done some really nice work on these observations of an infrared luminous red transient, and then she is very close to publishing on about the results from this program here. Okay, so I'll just wrap up with a summary here. So, yeah, I'm really excited about these synergies between these infrared and time domain observations, specifically with Rubin, Roman, and JWST, since I think this will really drive forward this exploration of our explosive and dusty cosmic origins. So the first thing I talked about, kind of revisiting the life cycle of stars and dust. Despite the importance of this question, it's still unclear what the origins of dust are. And what I'm interested in doing is doing infrared time domain observations to investigate these things, dust, stellar evolution, and cosmic origins. Okay, I talked a lot about carbon-rich Wolf-Rayet stars. Um, we've found some super interesting stuff. These WC stars seem to be a significant and early source of carbon-rich dust, and is enriching the interstellar medium with its carbon-rich aromatic compounds. We found these very clear pH features from the surrounding dust shells. And then again, I'm very excited about what we're going to have very soon with Rubin and Roman, and the combination with JWST to explore this landscape of infrared transients and probe this transient dust production and chemical enrichment from all these different types of, I guess, yeah, supernovae as well. There's lots of interesting things to do, but the non-supernovae, stellar eruptions and explosions, I'm very much looking forward to. All right, so with that, yeah, I want to thank you all for your attention, and yeah, super happy to take any questions.
Thank you so much, Ryan, for the description of these amazing data sets and the associated simulations and the future. It's really, really exciting to see. If you have questions, please raise your hand. You can also use the chat. I have several questions myself, but I want to give a chance to other people to ask questions, if there are any. Okay, so we have one from Nancy Morrison. So could small ground-based telescope up to, say, 1 meter, equipped with quality near-infrared cameras, contribute to infrared transient discovery and follow-up?
Yes, absolutely. In fact, yeah, I wish we had more of those 1 meter telescopes with near-infrared cameras, because I think it's these smaller platforms that are they're much more flexible in their observing time, um, and more you can follow up things more rapidly because of just the access to those facilities. So yeah, absolutely. I think that's those types of platforms are going to be crucial for doing follow-up, since I think that's yeah we'll be able to respond more quickly with those facilities. I think the challenge there is that infrared detectors are expensive, and so a lot of smaller telescopes or 1 meters and even less than that they're typically equipped with optical CCDs. But there are, yeah, I think there still are a number of 1 meters with near-infrared imaging capabilities, and it's that's definitely a capability that's important in following up these things. And I guess the challenge too is there's not really it's hard to do near-infrared wide field survey. I mean, I guess there's surveys like Prime that's doing it. Uh, there's surveys operated out of Palomar like Winter, which is doing like a near-infrared H-band survey. But there's not too many of those, and it's difficult to achieve the depth to sensitivity to identify these things. But dedicated follow-up is definitely yeah. something very important to do, and that can really significantly contribute to this. So yeah, that's a good question.
Thank you. Do you have other questions for Ryan? So I was wondering if saturation due to the bright star in the center may be an issue with Rubin, and how do you think that will affect the analyses?
Yeah, this is a good point. There's multiple things that could cause issues because of saturation. Like with Rubin, if you have a saturated source, it's going to make it difficult to do image differencing, or you're going to have a lot of weird, funny artifacts with Rubin. Um, and so the really bright stuff, I think that's not going to be super well suited for Rubin and Roman. But the idea is like we're looking for things like these dusty Wolf-Rayet stars or other like maybe if they're analogs within our own galaxy. Like there's a handful of stellar mergers as well within our own galaxy that may saturate with Rubin. Uh, we want to find extragalactic analogs of these or extragalactic carbon-rich Wolf-Rayet outbursts where they probably won't saturate, but they'll also you won't be able to see those nice dust shells around them. So looking at distant sources kind of resolves that issue of saturation. But yeah, I think looking at any bright source is going to be challenges there with identifying them with Rubin and Roman. Those are just hard in general for doing time domain astronomy, looking at bright stuff.
Okay, thank you. Do you have questions from other people? While you think about your question, okay, I see questions now. So, Sergio?
Yeah, I was wondering if, by the way, great talk. I was wondering if you also are in contact with people doing some experiments in the laboratory to try to understand the composition of this dust and
Yeah, that's a super good question. Riko Seno, who's at the University of Tokyo, her PhD supervisor is Itsuki Sakoan at the University of Tokyo, and one of the things he's doing is lab-based experiments to see if they can reproduce, yeah, things that produce these unidentified infrared bands or pHs. Although there's a number of groups I think that do laboratory work. Um, I haven't interacted with them like in that much in depth, but I think that's a crucial connection to make because with this new observing or there's new capabilities with JWST, we can see things that we haven't seen before. And it's definitely a good idea to catch up with what the latest is of the experimental work to see if we can yeah, figure out what's going on or figure out what all these features are associated with. So if there's any suggestions or recommendations on which groups to reach out to or maybe what papers to follow up on and with the latest experimental results, I'd
Mhm.
definitely be open to that. But yeah, I think that's going to be a crucial part of understanding what we see moving forward is the lab-based experimental work on not just the hydrocarbons, but other interesting uh, chemistry that we see with JWST.
Because I guess it's not only of interest for you for the work you are doing, but also for them because they can see features that will help them to understand better all the things that they are interested, no? So maybe it's also.
Yeah, yeah, exactly. And yeah, one of the exciting things too or one of the cool things about WR140 is that it's we pretty much have the timing nailed down yeah, super well. We know when it's going to form dust. We know when it's going to yeah, enter a periastron passage. So if the lab-based experiments can tell us like, okay, we want to study like what the signatures of dust formation at this particular time, we can do that. We know when it's going to form. We know how old it's going to be at a certain time because of how well the orbit is characterized and the dust shells that we see. Um, so we can use that as our astrophysical laboratory to validate some of these theories. So
That's really
yeah,
amazing. Yeah.
it's really a nice system, and it's a good it's a good time um, to start. I'm sure those conversations have already been started in other contexts, but to really like start to solidify that connection to help provide the observational evidence to those groups, and then vice versa to for them to help explain what we're seeing.
Okay, thanks.
Yep.
Kunal?
Yes, thanks for the nice talk. You discussed the case of Wolf-Rayet 140 and then also how you see similar signatures in the early universe. So I was wondering if you have any thoughts on how much of a role would metallicity play given Wolf-Rayet 140 is in the galaxy and then this early source is quite early. Uh, and then we have some sort of continuum because we have LMC, SMC, which are slightly lower. So can we bridge the gap in metallicity enough to understand, to link the two very nicely?
Yeah, that's a super good question. So, right. So I only showed you one source or the follow-up and kind of deep analysis of WR140, which is inner galaxy in this solar metallicity environment, which is not is very different, likely from what the early universe environment is like probably very low metallicity, and that likely affects the type of Wolf-Rayet star that you get. Um, so. We had also done some observations with Spitzer of extragalactic carbon-rich Wolf-Rayet stars in lower metallicity environments, and we found that those can also form dust. In fact, one of the follow-up observation, or one of the targets for follow-up observations that we did with JWST is of a extragalactic carbon-rich Wolf-Rayet binary in a lower metallicity environment, I think like zero point 0.5 solar, so not quite a direct analog to the low metallicity environment, but we see evidence that this can form a lot of dust, but it's hard to really bridge that. Um, yeah, to bridge that because you really are relying on your stellar evolution models, and with kind of you also need to incorporate binary interaction. So the things that we have been looking at is using BPAS, the binary population stellar synthesis models, um, to see what the population of Wolf-Rayet stars looks like as a function of metallicity. And in our analysis of that, it does seem like when you go to lower and lower metallicities, you get you don't get as many carbon-rich Wolf-Rayet stars, which will affect the total input from these sources. So that's still worth revisiting, and how much in this connection of yeah, just bridging the solar to subsolar low metallicity population of Wolf-Rayet stars that you can get. There might be things that we're missing. That analysis was done like 5 years ago, so that's something I'd be interested to revisit.
Cool. Thanks.
Yeah, thanks, Kunal. That's a good question.
Dietrich?
Exciting story, very nicely told. Thank you very much for that.
Thanks.
How would you compare luminous blue variables to Wolf-Rayet stars as dust factories? Because LBVs also kick in early.
Yeah, that's a really good question. I think LBVs are pretty promising sources of dust too, because they can form a significant amount of dust as we've observed. Uh, I think, yeah, I was thinking of trying to have like the best way to study those and compare them to Wolf-Rayet stars, and that's actually one of the focuses of our follow-up program for this cycle 4 program that we have to follow up. I'm not going to. Oh, yeah, actually, it's right here. So this one, LBVs are part of this census, so we're going to see if we can get a better idea of how much dust they form by looking at a number of those sources. It's Yeah, they could be comparable to the dust production from Wolf-Rayet stars, but from my understanding, I think LBVs primarily form silicate-rich dust because it's in an oxygen-rich environment. So there still could be a question of, yeah, you could get a lot of dust production from LBVs, but perhaps the carbon dust, they may primarily come from these carbon-rich Wolf-Rayet stars. But yeah, that's an important question. That's kind of what we're hitting at here with this question of like, well, let's not just look at the Wolf-Rayet stars, but let's investigate all other sources of eruptive mass loss from massive stars like LBVs. I think that one's a little more tricky because um, at least the LBVs that are known, they don't all show similar mass loss ejection rates. It's also not quite clear what the mass loss or eruption mechanism is of LBVs. So it's a harder question to frame, but it's also important because, um, observationally, we see that they form a lot of dust, and so we should really focus on those as as potential dust factories.
Yeah, I agree with what you said, everything. And in particular, that they may be chemically complementary.
Yes, exactly. Yeah,
Yeah.
if they're major sources of the silicate dust and then carbon-rich Wolf-Rayet stars, carbon-rich dust, yeah, you have a nice complementary sources of different types of dust grains that we see in the ISM. So yeah, I agree with that. Basically, what I'm thinking here is like, what are the other types of non-supernova sources that can form dust? So yeah, LBVs, maybe stellar mergers, carbon-rich Wolf-Rayet stars. Um, yeah, just trying to think outside of supernovae, what we can investigate and characterize systematically.
Thank you.
Yeah, thanks. Good question.
There's a question from Lydia in the chat. She wants to know if for systems WC plus O like WR140 that emit X-rays at periastron, if there are studies of the relation between the X-ray producing regions and the dust producing regions.
Yeah, that's a good question. There are, I think, and I see Peredur Williams is online. He might be better equipped to answer this question than me. But my understanding of this is that um, they are, let's see. No, I think I'm thinking of the optical emission and the dust production, but um, I think the X-rays dip when you see the dust production uh, kick up. But I think there is some kind of correlation. I don't, yeah, I can't recall off the top of my head since I hadn't been looking at the X-rays specifically. And I know Chris produced those models um, to investigate that. I think he was working on incorporating the infrared component of it, which is the dust production. But there's still it's very difficult to do to connect those two because of the different size scales of what's required. Like the X-rays are coming from the very inner colliding wind region, whereas the dust production is coming from much further out. But yeah, maybe I don't know. I see Peredur's on. I don't know if you, you want to add anything to that. Um, if not, I may defer to other papers to check that out. I know Andy Pollock has also been looking at this a lot.
Okay.
Oh, I see. Is Peredur? We can't hear you, Peredur. If you're.
Yep, sorry. If I can add then, yes, you're quite right. The dust is formed quite far from the X-rays are formed. But there is this great dip in right at periastron in the luminosity, that is the extinction corrected X-ray emission. And Andy Pollock has laid a paper on this and showing that really what's happening is in this phase range, you've got additional cooling coming from little sub-peaks on emission lines. And this is most easily observed in the yellow spectral region 5696 carbon-free, and you can also see it in the helium-1 metastable line at 1.08 microns.
Yeah, thanks for covering that.
Thank you. 30-second question. So you didn't talk about how the dust production of red supergiant compares to the AGBs and the WCs. Can you say something about that?
Yeah, sure. Yeah, the red supergiant dust production is actually, I think, like an order of magnitude lower than the population of AGB stars and carbon-rich Wolf-Rayet stars. So those don't seem to contribute super significantly, at least based on our analysis. And so yeah, the dust production isn't quite as efficient from red supergiants. I mean, they have faster winds than AGB stars, but the dust production rates, I think, are like they kind of max out maybe at 10 to the -7 solar masses a year. I think that's, yeah, just thinking off the top of my head. But yeah, those seem to be relatively low compared to other sources. But yeah, good question. I forgot to go into more detail about the red supergiants.
Thank you. Andreas, you want to very quickly say your comment?
No, not important. I think Lida had an actual question.
Okay. I don't see it. Dina, can you open your mic?
Oh, no, maybe he was thinking about her previous question about.
No, thank you for answering my question. Everything is fine. Wonderful talk. Thank you.
Yeah, thanks, Lita. But yeah, I agree with Andreas's point here, right? Yeah, they have a lot of carbon in their photosphere, in their winds, and so they're a really promising source of carbon-rich material pre-supernovae. So I totally agree with that statement there.
Okay. So we've 1 minute after the hour. I actually have one more comment, so you can stay just a few more minutes, or whoever wants to stay. Can you do that? Just
Sure.
it's just a comment that in the FANGS survey of nearby galaxies, which have been observed with JWST, they have been finding these 10 micron emitters. And I was wondering if maybe, and with broadband JWST imaging, and there are not very many, but there are some, and I was wondering if maybe those could be associated with clusters that have WC stars, since you were mentioning this sulfur 4 feature at 10 micron, around 10 micron.
Yeah, there's a lot that those sources could be. Like, yeah, without spectroscopy, it's hard to identify. There's a lot of things that are bright at the mid-infrared, and also 10 microns that aligns with the 9.7 micron silicate feature. So that might be discrepant from what we would expect for carbon-rich Wolf-Rayet stars. And yeah, and that sulfur 4 feature at 10.5 microns, it's fairly weak compared to the continuum emission. So I don't think it would be dominated by, or I don't think the 10 micron broadband image would be dominated by that sulfur 4 emission line, not like neon 2 at like 12.8 microns, where that filter, it might be dominated by that particular emission. So although I haven't thought about that in detail, but it might be interesting to look into the FANGS observations a little more, to look at these dusty, presumably dusty things popping up at 10 microns, because it probably is indicating some source of significant dust production, or if there are clusters, something in that, must be causing that level of obscuration. It could be just dust continuum emission. But yeah, I should follow up in more detail. If they're just popping up at 10 microns, then maybe something more interesting is happening there. It could be emission feature related.
Yeah, it's not systematic. There are only a few, but yeah. Okay. Thank you. So let's thank Ryan again for his talk, and I guess we can stop the recording now, Sergio. I will be available on YouTube if